I've got my pieces cut out. I'm thinking, for some reason I got attracted to arranging them in that sort of a picture there, but there was no law that said I had to make a spiral. Once I've got them cut out, I can see in, you know, all of the choices. Oops, that was a bit, sloppy cutting. I've got a lot of choices in how I put these guys down, actually. I didn't need to make them match their orientations or anything. I suppose I could try to push infinity into the corner if I wanted to by, you know, putting my tiles preferentially to the top left in the box, so it's not fitting quite perfectly. But let's put, so what was this guy? That was 1 over 16. And here's 1 over 32. And an old 1 over 64. And so there's my missing 64th, which I could keep on filling if I had even smaller tiles for smaller fractions. What else can I do? I guess of course there are only so many ways that these can go together. I could try putting all the square guys in a row, and then where does that leave me? Can I put all the rectangular guys together too? So I already decided where the first rectangular guy was going to go, that big orange half, so I'll put his little red quarter next to him, tuck him under there. And move that guy. There we are. Well, I kind of like that one too, because it's, you know, as you can imagine how it would continue, the rectangles are getting smaller and smaller, marching off into the corner, and then the squares are jumping into the corner as well. And so here we see, you know, 2 sequences of the rectangular guys. Remember, those were the fractions. Every second fraction was a rectangle, right? 1/2, not a quarter, but an 1/8. Not a 16th, but a 32nd. So those guys are there. And then the fellows that came out square, the way I was shading, were the 1/2 by 1/2. So it was a quarter, the blue quarter, the green 16th, skip the 32nd, and then the black 64th. So now we've arranged them so that we can see the sum of these rectangles. Looks like it's converging as well, right? So if I just drew more and more rectangles, let me just color in here, or draw with my pen. The next rectangle would be here, and there'd be a square there, and then we'd do it again with a rectangle here and a square there. And so the sum of the rectangular contributions seems to be adding up to some constant value as well, or approaching it as close as you like. And at the same time, the sum of the square guys is adding up to whatever is left over. So a quarter plus a 16th plus a 64th plus whatever this is and that. And then when you put them together, you get 1. So it looks like there's something we could look for in this picture as well. Notice that each of these terms, the squares, are only half as big as the rectangle that went before. So I had the orange half, and then his next guy, his next friend was square, so that was the blue square, half as big. The 8th was a red rectangle. The 16th was the green square, half as big. So these guys are all half as big as those guys. So if you worked on the details a little bit, you could probably argue that this sum is twice as big as this sum. So then if you saw this chain of rectangles was forming some infinite chain that still fit in the box, and complementary bit was this infinite chain of squares, then the contribution from the rectangles, if they're all twice as big as their next square, that means that the rectangles, whatever they add up to, is twice as big as whatever the squares add up to. The whole thing fits in the one box, right? So two of these, one of those, I guess that means this is 2/3 and the squares add up to 1/3. That's kind of fun. And I suppose then if you try to rearrange these in other ways, you could probably also find other patterns and see some other ways in which the infinite sum fits in the box.